Here are the top 10 things you need to know in order to solve different types of inequalities. Must know number 1. What is an inequality? Starting with the definition, an inequality compares two values and shows whether one is greater, less, or possibly equal to the other. And now let's fill out a chart where I'm going to show you the 4 different symbols that are used when writing inequalities. And now in this table that I've created, let's look at what all 4 of these symbols mean. This first symbol is the greater than symbol. And here's an example of an inequality that uses that symbol. When reading from left to right, this inequality says that x is greater than 5. So some examples of x values that would satisfy this inequality would just be values that are greater than 5. So for example, 6, 7, 8, and so on. Any value of x greater than 5 would satisfy that inequality. And there's a great way to describe the set of all x values that satisfy this inequality. We can write them in interval notation. The interval of x values that are greater than 5 would be x values that fall within the interval between 5 and infinity. Notice inside of round brackets, I wrote the lower boundary for the interval, 5, comma, the upper boundary for the interval, infinity. Any x value between 5 and infinity, not including 5 and infinity, would satisfy that inequality. And the fact that these brackets are round is important. That tells me that these values, 5 and infinity, are not included in the interval of x values that satisfy this inequality. Right? We can't include 5 in the interval because 5 is not greater than 5. It's equal to 5. But any number between 5 and infinity, if I sub it in for x, it would make this inequality true. And now let's look at the next symbol. This symbol here is the less than symbol. An example of an inequality using the less than symbol would look like this. We're reading from left to right, it says that x is less than 5. And examples of x values that would satisfy this inequality would be any number less than 5. So for example, 4, 3, 2, and so on. And once again, I could describe the set of values described by this inequality using interval notation. The interval of x values that are less than 5 would be the x values that are between negative infinity and 5. Any x value between this lower and upper boundary, not including either of those numbers, would satisfy this inequality. And then the next symbol, notice we have the greater than symbol with a line underneath of it. That means greater than or equal to. And here's an example of an inequality using that symbol, where this one, as I read it from left to right, states that x is greater than or equal to 5. So any number that is bigger than 5 or equal to 5 would satisfy this inequality. So examples of numbers would be 5, 6, 7, and so on. And this set of numbers that describes this inequality can be described in interval notation. It's going to look really similar to when x had to be bigger than 5, but this time we want to include 5 in the interval. So notice when I write an interval notation, this time I'm going to use a square bracket at 5. That includes 5 in the interval. Comma, the upper boundary is still infinity, and you always use a round bracket at infinity in interval notation. So when looking at this interval, I know that any x value between 5 and infinity, including 5 itself because of the square bracket here beside the 5, would satisfy this inequality. And now on to the last symbol. This symbol is the less than or equal to symbol. So for this inequality, reading from left to right, it would say that x is less than or equal to 5. So the set of x values that this inequality is describing would be, for example, any x value 5 or less. So 5, 4, 3, and so on. And in interval notation, we could say it's the set of values between negative infinity and 5, but we want to include 5, so I'll put a square bracket at 5. So this interval describes this inequality. It contains all of the values that are less than or equal to 5. And before moving on, let me shrink this and give you one important tip. Inequalities don't always have to be read from left to right. They can be read in either direction, as long as you remember the symbol always opens towards the larger value. So for example, this inequality could be read in 2 different ways. Reading this from left to right, I can interpret the symbols as described in this chart. This is the less than symbol, so I would read it as 5 is less than 7. Or this could also be read from right to left. But when reading it from right to left, you have to notice that the symbol opens up towards the bigger number. So this inequality is stating that 7 is bigger than 5 because it's opening towards the 7. So in reading from right to left, that's how we would read it. We would read it as 7 is greater than 5. Notice that both of these statements are saying the exact same thing, but getting comfortable reading inequalities in both directions will help you get more comfortable with the symbols. Must know number 2, graphing inequalities on a number line. Equations tell us exact values, but inequalities describe a range of values. Number lines are a great way to visualize these ranges. And now let me take you through a few examples where we use a number line to graph an equation and two different inequalities. Starting with this equation that I have here, x equals 3, this describes one exact value. It says x is equal to 3. So that would be really easy to represent on a number line. I just find the x value of 3 and then draw a dot above it. And then the next two examples, they're not equations, they're inequalities. So they represent ranges of values. Looking at this first inequality, it states that x is greater than negative 2. And then what I could do is above this number line, I could graph a line that describes the set of all x values that are greater than negative 2. To do that, I start by finding the value of negative 2 and drawing an open circle above negative 2. And then I'll graph a line that extends across all of the values that are greater than negative 2. Well, notice all of the values to the right of negative 2 are greater than negative 2, so I'll draw a line that extends above all of those numbers. And that line would continue infinitely forever to the right. And the fact that I chose to put an open circle above negative 2 is important. The inequality says I just want the numbers greater than negative 2. So you use an open circle if the number is not included in the interval. And negative 2 itself is not bigger than negative 2, so it can't be included in the interval, which is why there is an open circle above negative 2. So this inequality, x being greater than negative 2, can be visualized using a number line, but we could also describe the set of values using interval notation. By inside of circular brackets, writing the lower boundary of the interval, which I can see is negative 2, comma the upper boundary. Well, this line is going to continue forever towards infinity, so I'll say the upper boundary is infinity. And remember, these round brackets mean that these boundaries, negative 2 and infinity, are not included in the interval. But when we look at our third example, it says that x is less than or equal to 3. So on a number line, I could represent that interval of values by finding the number 3, and then putting a closed circle above 3, and then drawing a line that extends above all the numbers that are less than or equal to 3. Well, all the numbers to the left of 3 are less than or equal to 3, so I'll draw a line that extends above all those numbers. And this line would continue infinitely to the left. And notice this time, I used a closed circle above the 3. That's because I wanted not only the values less than 3, but also the values that are equal to 3. So I wanted to include 3 in the interval. You always use a closed circle if the number is included. And then once again, I could describe this inequality not only visually with a number line, but also I could describe the set of values that are less than or equal to 3 by writing them in interval notation. The set of numbers less than or equal to 3 would be the numbers between negative infinity and 3. I'll put a round bracket at the lower boundary of negative infinity, comma, at the upper boundary of 3, I'm going to put a square bracket because I want to include the value of 3 in the interval. Must know number 3, solving linear inequalities with one variable. Solving linear inequalities is the exact same as solving linear equations, except when multiplying or dividing by a negative, you must flip or reverse the inequality. So let's take a look at a couple examples. In this first example, we're trying to solve this linear inequality that just has one variable, meaning we want to find the set of x values that make this whole inequality true. So what set of x values, when I add 3 to them, do I get a number that is greater than 7? And remember, because this is an inequality, not just an equation, we're not just going to get like one exact answer. We're going to get a range of values that we can describe as a set using interval notation. And to find that interval of x values that satisfy this inequality, we can solve this just as if it was an equation. I can isolate this x using inverse operations. Right now there is a 3 being added to the x. So I can remove that 3 by subtracting 3 from both sides. The 3's on the left will cancel, leaving me with the inequality x is greater than 7 minus 3, which is 4. And this is in fact the answer to the inequality. This is the interval of x values x values greater than 4, they would satisfy the original inequality. And anytime you finish solving an inequality, you should test it out to make sure you have the right interval of values. Pick any x value that's greater than 4. Well, 5 is bigger than 4, so let me test out 5 in this original inequality. Is 5 plus 3 greater than 7? Yes, 8 is greater than 7. And in fact, any x value greater than 4, if I sub it in for this x, when I add 3 to it, it will be greater than 7. So I know I have the right interval of x values here. But there are a couple other ways we could describe this answer. I could graph this inequality on a number line. To graph the x values greater than 4, I would put an open circle at 4 because I don't want to include 4, and then draw a line extending out to the right infinitely. Or the most common way to describe the answer to an inequality is to write the answer in interval notation. The interval of x values described by this inequality and by this arrow are the x values somewhere between 4 and infinity. And I don't want to include 4 or infinity, so round brackets at both 4 and infinity. So any x value chosen within this interval, any value between 4 and infinity, not including 4 and infinity, subbed in for this x, will make this inequality true. And let's try one more example. Once again, this example is a linear inequality with only one variable. When that happens, solve it just like it was an equation. Let's try and isolate this x using inverse operations. On the left, I'm adding 5 to the x, so I'll start by subtracting 5 from both sides. On the left, the 5's cancel, leaving me with negative 2x is less than or equal to 8. And then on the left, I'm multiplying the x by negative 2. The inverse of multiplying by negative 2 is dividing by negative 2. So I'll have to divide both sides by negative 2. But the golden rule of solving linear inequalities is that when you multiply or divide by a negative, like we just did here, on the next line, we're going to have to reverse the inequality symbol. So yes, these negative 2's cancel, leaving me with x is not less than or equal to negative 4. I have to reverse it. Make it x is greater than or equal to negative 4. And this inequality itself is the answer to the original inequality. Any x value greater than or equal to negative 4 will make this inequality true. We could test it out. An x value that's greater than or equal to negative 4, well, 0 is greater than or equal to negative 4, so let me test 0. Is negative 2 times 0 plus 5, is that less than or equal to 13? Well, this would simplify to 5 is less than or equal to 13, which is of course true. And when solving an inequality, it's good habit to state your final answer in interval notation. So let's actually graph this on a number line first, and then use that to help state the interval of x values. The x value is greater than or equal to negative 4. I would put a closed circle at negative 4 because I want to include negative 4 in my interval, and then extend a line out to the right infinitely. Notice this line covers all of these x values that are all greater than or equal to negative 4. And now let's also state the final solution in interval notation. The interval of x values greater than or equal to negative 4 would be the numbers from negative 4, including negative 4, so square bracket at negative 4, all the way up to infinity. Choosing any x value from within that interval will satisfy the original inequality. Must know number 4. Compound inequalities using OR. These types of compound inequalities are called disjunctions. And compound inequalities are just if you're considering more than one inequality at the same time. And for OR compound inequalities, you solve each part separately, and then the solution set includes all the values that satisfy either part of the inequality. This is the union of the two sets. Now let me take you through a few examples so you can see how these compound inequalities work. Notice in example 1, it says 5x minus 3 is greater than negative 18, or negative 2x minus 1 is greater than 15. Now when solving these types of compound inequalities, you have to start by solving each of the inequalities separately. Starting with 5x minus 3 being greater than negative 18, I'll solve that inequality by isolating this x on the left side of the inequality. I'll add 3 to both sides, leaving me with 5x is greater than negative 15, and then I'll divide both sides by 5, giving me x is greater than negative 3. So this is the solution to the first inequality in our compound inequality, but my final answer is going to be not only this set of numbers, it's also going to include the set of numbers that satisfy the second inequality, so I have to solve this second one as well. I'll isolate this x, first by adding 1 to both sides, giving me negative 2x is greater than 16, and I'll divide both sides by -2. And I have to remember when dividing by a negative, I have to reverse the inequality. So it'll be x is less than -8. So my final answer is x is greater than -3 or x is less than -8. Let me represent this on a number line, and then we'll combine these answers into interval notation. I've just made a rough number line with key values labeled. Let me graph this inequality on the number line. The set of numbers greater than -3, I would draw an open circle at -3, and then extend a line out to the right so that it covers all values greater than -3. And for x being less than -8, I can graph that on a number line by putting an open circle at -8, and then extending a line above all numbers that are less than -8. So the final answer to this compound inequality would be the set of numbers that are covered by either of these two lines. So that would be the interval of numbers between -infinity and -8, or, and we use a u to represent or, that's the union of the sets, the interval of numbers between -3 and infinity. So this is how final answers are commonly represented for compound inequalities. They're written in interval notation. And this u means that any number within the first interval or the second interval is considered a solution to the compound inequality. Because as long as you pick a number within the first or second interval, it's going to satisfy either the first inequality or the second one. It doesn't have to satisfy both of the inequalities. It just has to satisfy one or the other. So for example, if you picked a number in this second interval between -3 and infinity, we could pick 0, that's between -3 and infinity. If I subbed 0 into this first inequality, I would get -1 is greater than 15, which is of course not true. But if I subbed 0 into this inequality, I would get -3 is greater than -18, which is true. So that's just demonstrating that if you pick any number in this interval, it will satisfy this inequality but not the other. But that's fine for or compound inequalities, because the final solution set just has to satisfy either the first one or the second. It doesn't have to satisfy both. Now let me shrink this and let's do another example. In this example, I need the set of n values that satisfy this first inequality or the second inequality. So we'll solve them both separately, starting with the one on the left. I can isolate the n by multiplying both sides by 3, and I get n is less than 9. And then for the second inequality, the one on the right, I could isolate the n by dividing both sides by -5, and then because I divided by a negative, I'll have to reverse the inequality, giving me n is greater than 2. So the solution to this compound inequality is going to be the interval of n values less than 9, or the interval of n values that are greater than 2. Let me graph both of those on a number line. Now the solution to this compound inequality are the numbers covered by either the first inequality or the second one. And notice if I were to combine those lines together they extend infinitely to the right and infinitely to the left. So my solution would be the interval of numbers between -infinity and infinity. Now let me shrink this and let's do one final third example. Once again, we have an or compound inequality. We'll solve each of the inequalities separately, starting with the one on the left. I'll add the 9 to the other side, giving me 3x being greater than or equal to 18. And then I'll divide both sides by 3, giving me x is greater than or equal to 6. Solving this second inequality, I'll subtract this 4 to the other side, giving me 2x is greater than or equal to 6. And then I'll divide both sides by 2, giving me x is greater than or equal to 3. So any x value that is greater than or equal to 6, or greater than or equal to 3, is a solution to this compound inequality. Let me graph both of those ranges of values on a number line. And my final solution set is just going to be the values that fall underneath either the blue line or the yellow line. So notice if I combine those together, the blue inequality just absorbs the yellow inequality. X being greater than or equal to 6 is just a subset of the x values that are greater than or equal to 3. All the values that are greater than or equal to 6 are also greater than or equal to 3. So I can combine those into one final answer just by stating the interval of values that are greater than or equal to 3. Meaning my final solution are the set of values between 3 and infinity. And notice I used a square bracket at 3 because I wanted to include that in the interval. Any value chosen within that interval will satisfy either the first inequality or the second, or If it's 6 or bigger, it'll actually satisfy both. But for this one, we just need it to satisfy one or the other, which is why this whole interval describes the solution set to this compound inequality. Must know number 5, compound inequalities of the AND type. For AND inequalities, you solve each part separately, but the solution is the set that satisfies both parts of the inequality. So it's the intersection of the two sets of solutions. So let's have a look at a few different examples. In this first example, we're trying to find the set of values that satisfies both the first inequality and the second inequality. In order for a number to be part of the solution set, it's not enough for it to just satisfy one or the other. It has to satisfy both. So we'll start by solving both of these inequalities separately. Starting with this first inequality, I'll rearrange to isolate x on the left side by first taking this -3 and adding 3 to the other side, giving me 6x is less than 9 plus 3, which is 12. And then I'll divide the 6 to the other side, giving me x is less than 12 over 6, which means x has to be less than 2. And now solving the second inequality, I'll isolate the x by subtracting 7 to the other side, giving me 2x is greater than or equal to 3 minus 7, which is -4. And then I'll divide this 2 to the other side, giving me x is greater than or equal to -4 over 2, which means x is greater than or equal to -2. And because this is an AND compound inequality, my final solution set has to be the intersection or overlap of these two ranges of x values. So it will help if I graph both of these intervals on a number line. And now I need to figure out, using this graph, what's the set of numbers that are both less than 2 and greater than or equal to -2? Well, that would just be the overlap in these two lines, which would be this section right here. I'll combine them together on the number line in blue. So my final solution to this compound inequality would be the numbers between -2 and 2, including -2, but not including 2, which is why I have a square bracket at -2, but a round bracket at 2. Notice any number within this interval between -2 and 2 would be both on this line and that line, which means its value would satisfy both the first inequality and the second inequality. We could even pick a test value. A number between -2 and 2 could be the number 0. If I subbed 0 in for x into the first inequality, I would get -3 is less than 9, which is true. And if I subbed 0 in for x into the second inequality, I would get 7 is greater than or equal to 3, which is also true. It satisfies both of the original inequalities. And that's what has to happen when solving a compound inequality with the word AND between the two inequalities. All the values in the final answer has to satisfy both the first one and the second one. Let me shrink this and let's try another example. In this example number 2, we have a compound inequality with the word AND between them. So our final answer will be the set of values that satisfy both the first inequality and the second inequality. We'll start by solving the first inequality. To isolate this x, the first thing I would do would be divide both sides of this equation by -3. And when dividing by a negative, remember the golden rule, we have to reverse the inequality symbol. So instead of less than or equal to, it's now going to be greater than or equal to -6. And then I could just subtract 5 to the other side, and then divide the 2 to the other side. X is greater than or equal to -11 over 2, which as a decimal I could write as -5.5. So any x value greater than or equal to -5.5 would satisfy that first inequality, but we need the set of values that not only satisfy the first one, but they have to satisfy the second one as well. So let's solve the second inequality. I could start by dividing both sides by 2. When dividing by a positive value, we don't have to reverse the inequality. It stays as x minus 7 being greater than -3. And then add 7 to the other side. X is greater than -3 plus 7. And -3 plus 7 is 4. So the x values bigger than or equal to -5.5 satisfy the first inequality. The x values bigger than 4 satisfy the second inequality. But what we need to find for this question is the set of x values that satisfy both of those inequalities, the intersection of these two solutions. So I'll graph both of those ranges of values on a number line. My final solution to this compound inequality needs to be the set of values that satisfy both of the original inequalities. So graphically, that would be where these two lines intersect, which would be this section over here. Combining them together on the number line below, I would have an open circle at 4, and then it would extend out to the right, which means my final solution would be the interval of values from 4 to infinity, not including 4 or infinity. Picking any number between 4 and infinity would satisfy both the first inequality and the second inequality. And now let me make some room so we can do one final example where I show you a double inequality. This example is called a double inequality because we see two inequality symbols in the same line. This can be thought of as an AND compound inequality. 3x minus 7 has to be greater than or equal to negative 4, but also less than 8. But we can solve them actually both at the same time when it's written as a double inequality. Whatever I do to any one section of this inequality, I have to do to all three of them. So to isolate this x in the middle, I could start by adding 7 to all three sections. And then simplifying, I have 3 is less than or equal to 3x is less than 15. And to isolate this x, I'll now divide all three sections by 3, leaving me with 1 is less than or equal to x is less than 5. So this statement reads that x is greater than or equal to 1 and x is less than 5. So my final answer to this original double inequality are the x values that are greater than or equal to 1 and less than 5. To write that set of values in interval notation, it would be helpful if I first graph them on a number line. My final solution set is going to be the set of values that fall on both of these lines. It's the intersection of those two lines, which would be all the numbers between 1 and 5, including 1, but not including 5. So let me give myself a bit of room to write that final answer in proper interval notation. The solution is the interval of x values between 1 and 5, including 1, so square bracket at 1, and not including 5, so round bracket at 5. Subbing in any number between 1 and 5 in for this x in the original double inequality is going to make the middle value be greater than or equal to negative 4 and less than 8. It'll satisfy both parts of that double inequality. Must know number 6, inequalities with an absolute value. And first of all, before doing this section, remember the absolute value of a number is just that number's overall distance from 0 along a number line. And that distance is always expressed as a positive value. So the absolute value of, let's say, negative 5 is just 5. And if you have an inequality that contains an absolute value, you're going to have to create a compound inequality. There are two cases we need to consider. Case 1 is if we have an absolute value of a variable less than a constant. Now, because taking the absolute value of any number turns it positive, to find the full solution set for this inequality, we have to turn it into a double inequality. X would have to be greater than negative a and less than positive a. Notice I turned this into an and compound inequality. And now let's do an example so you can see how this works. I want to determine for what values of x is the absolute value of x minus 3 less than or equal to 5. Because it's a less than, I need to turn it into this double inequality. The absolute value of x minus 3 would be less than or equal to 5 if x minus 3 was both bigger than or equal to negative 5 and less than or equal to 5. So as long as x minus 3 is between these two values, negative 5 and 5, when I take its absolute value and I make it positive, it's going to make it less than or equal to 5. And then let's actually solve for x in this inequality. I'll add 3 to all three parts of it. Then this would simplify to negative 2 being less than or equal to x being less than or equal to 8, which means my final solution set would be the set of x values that are greater than or equal to negative 2 and less than or equal to 8. And this would be easy to graph on a number line. I can see that the intersection of those two ranges of x values is exactly as described in this double inequality. X is between negative 2 and 8, including negative 2 and 8. And I can show that overlap on the number line, which makes my final solution the interval of x values between negative 2 and 8, including negative 2 and 8, which is why I've put square brackets at both negative 2 and 8. Picking any test value between negative 2 and 8, so for example, negative 1, if I sub that in for this x, I would get the absolute value of negative 4 being less than or equal to 5. And the absolute value of negative 4 is 4, and 4 is less than or equal to 5. And now let's look back at the second case. What if we have the absolute value of a variable greater than a constant? To evaluate this type of inequality, we once again turn it into a compound inequality, but this time an OR inequality. The absolute value of x would be greater than a if x was greater than a, or if x was less than negative a. And let's do an example so you can see how that works. The first thing we'll want to do in this example is to isolate this absolute value term. So I'll add 9 to the other side, and then I'll divide the 3, leaving me with the absolute value of 2x minus 5 being greater than 7. I need to turn this into an OR compound inequality. The absolute value of 2x minus 5 would be bigger than 7 if 2x minus 5 was in fact bigger than 7, or if 2x minus 5 was less than negative 7. So of course, if 2x minus 5 is bigger than 7, then its absolute value will also be bigger than 7. But if 2x minus 5 is less than negative 7, so let's say it's negative 8, when I take its absolute value, it's going to become positive 8, which is also bigger than 7. So any x value that satisfies that one or that one will be a solution to the original inequality. So let's solve both of these separately. Starting with the one on the left, I'll add the 5 over, and then divide the 2, giving me x is greater than 6. And then solving the second one, I'll add 5 over, and then divide the 2, giving me x is less than negative 1. So any x value that is greater than 6 or less than negative 1 will satisfy this original inequality. And let me combine these answers together in interval notation, first by graphing them on a number line, and let me describe that solution in interval notation. X can be within the interval of numbers that are less than negative 1, so from negative infinity to negative 1, or, which we use the U, the union symbol for, or within the set of values that are greater than 6. So that would be from 6 to infinity. Must know number 7. Linear inequalities with 2 variables. Up until now, all of the inequalities we've solved have just had one variable, and we could describe the interval of values for that variable that satisfies the inequality. But when we have 2 variables in our inequality, how we solve it is by first graphing what's called the boundary line, which will be a dashed line if it's not included in the solution set, and that will happen when the original inequality is just a greater than or less than symbol, but it will be a solid line if it is included in the solution set. And that will happen if the original inequality is a greater than or equal to, or less than or equal to symbol. And then step 2, after you've graphed the boundary line, you pick a test point on either side of the boundary line to test which side of it is the region that contains all of the points that make up the solution set. And then based on your test, you're able to shade the entire region that contains all of the solutions to the inequality. So let me make a bit of room and let's do an example. When looking at this inequality, the first thing that I notice is that there are 2 variables. So there's going to be an entire region of points that satisfy this inequality, which means to show the answer to this inequality, I'm going to have to shade in that region by first graphing the boundary line. And to graph the boundary line, I'll want to isolate this y in the inequality. So I'll take this negative 2x, move it to the other side, making it a positive 2x. And then I'll have to divide this 3 to the other side, making sure to divide both terms by 3. Giving me y is greater than 2/3 x plus 6 over 3, which is 2. And now that y is isolated, I can graph the boundary line. The equation of the boundary line is just this inequality, with the inequality symbol changed to an equal sign. And then to graph that line, I could plot the y-intercept of 2, and then use my slope of 2 over 3 to rise 2 and run 3 and plot more points. And now because the original inequality is a greater than symbol, that means all the points that lay on this boundary line are not going to be part of the solution. So I used a dashed line for the boundary line. And now in either the region above that boundary line or the region below that boundary line are all of the points that would satisfy the original inequality. We can just pick one point on either side and use it as our test value. Typically, if the origin is not on the boundary line, so the point 0, 0, we'll use that as the test value. So by testing it, what I mean is take the x and y value of the point 0, 0 and sub that into the original inequality and see if it's true. That would give me negative 2 times 0 plus 3 times 0 is greater than 6, which states that 0 is greater than 6, which is false, which means this point 0, 0 is not part of the solution set for the original inequality, which means none of the points on this side of the boundary line satisfy the original inequality, which by default then means all of the points on this side of the boundary line do satisfy the inequality. And you could see how when y is isolated, it's easy to know that it's the region above the boundary line, because it says all of the y values that are greater than that boundary line 2/3 x plus 2 satisfy this original inequality. So my final answer is just going to be me shading in this region above the boundary line. And that's how we express the solution to the inequality. And that's because any point that you would pick within that shaded region, no matter where that point is, its x and y values would satisfy that inequality. Must know number 8, systems of inequalities. A system of inequalities is when you have two or more inequalities with the same variables. And the solution to a whole system of inequalities is the region where all inequalities are true at the exact same time. It's the overlap of the shaded regions. So let's go ahead and try an example. In this example, notice we have two inequalities, both with the same two variables. So this is a system of inequalities. The solution to this system would be the set of points that satisfy both the first and the second inequalities. So I'll find the solution regions for both of them and then find where those regions overlap. Let's start with this linear inequality with two variables. Because y is isolated, I can see that its boundary line would be the line y equals a half x plus 5. I could graph that by plotting its y-intercept at 5, and then using the slope of 1/2 to plot more points. And when graphing the boundary line, because the inequality symbol is a less than or equal to, I want to include the boundary line in the solution, so I'll make it a solid line. And now the region that satisfies this inequality is going to be the region where the y values are less than or equal to this boundary line, which would be this region underneath the line. And if I wanted to, I could use a test point to verify that. I'll use the point 0, 0 as my test point. When subbing that into this inequality, it states that 0 is less than or equal to 5, which is true. And since that point 0, 0 makes the inequality true and it's underneath the boundary line, all other points in that region underneath the boundary line must also satisfy this inequality. So I'll shade in that region. And now let's consider the second inequality. This time, our boundary line is going to be the quadratic y equals x squared. So I'll graph that quickly. Notice I graphed this quadratic with a dotted boundary line because we just want the y values that are greater than x squared. We don't want to include the points that are on the quadratic. And now I have to decide, is the region above the quadratic y equals x squared, or the region below that quadratic, the region that contains all of the points that satisfy this inequality? Well, I can choose a test point. I'll choose this point 0, 1 that's above y equals x squared. When I sub that xy point into this inequality, it states that 1 is greater than 0 squared, which says that 1 is greater than 0, which is true. So since this point 0, 1, which is above y equals x squared, satisfies the inequality, all other points in this region would also satisfy this inequality, so I'll shade in that area. And then the final answer to this system of inequalities is the region of points that satisfy both of them. So that would be the overlap in these two shaded areas. That would be this area right here where the regions overlap. Any point within this region would satisfy both of the original inequalities, which is why it's a visual representation of the solution to this system of inequalities. Must know number 9, solving polynomial inequalities. When solving a polynomial inequality, you're going to first move all terms to one side. Second, you're going to get it into factored form to be able to determine its x-intercepts. And then third, you're either going to graph it or make a sign chart to help determine the solution. So let's look at an example. For this example, the first thing we'll want to do is get all the terms to one side, so I'll take both of those terms, moving them to the left. And now I need to factor this polynomial. I noticed that factoring by grouping would work. Taking a common factor from the first two terms, I could common factor out an x squared. And then from the last two terms, I could common factor out a negative 25, giving me this common binomial of x minus 3 between the two terms. So I'll common factor out that x minus 3, leaving me with x squared minus 25 as the second factor. And that x squared minus 25, that's a difference of squares. I could factor that further to x minus 5 times x plus 5. And the reason why we got this into factored form is because what we're going to do next is state the x-intercepts of this polynomial, which would just be the zeros of any of these factors. 3 would make the first factor be 0, 5 would make the second factor be 0, and negative 5 would make the last factor be 0. And now that I know the x-intercepts of this polynomial function, I should be able to sketch a rough graph of it, and then using the graph, figure out when that polynomial is greater than or equal to 0. But before I do the graph, you're going to have to know the end behavior of this function. Because this polynomial function is an odd degree polynomial with a positive leading coefficient, I know that means that the polynomial goes from quadrant 3 to quadrant 1. So let me make a rough sketch of the graph. The x-intercepts are at negative 5, 3, and 5, and I know it starts down in quadrant 3 and finishes up in quadrant 1. So it would roughly look like this. And this is the graph of this polynomial. And we're interested in figuring out when it's greater than or equal to 0. The values of x that satisfy this original inequality will be the values of x that make this polynomial be greater than or equal to 0. So just when is this polynomial above the x-axis? I could highlight those sections in blue here. So when the x values are between negative 5 and 3, or bigger than 5, notice that the polynomial's y values are greater than or equal to 0, which means the solution to this inequality is the interval of x values between negative 5 and 3, or from 5 to infinity. And because I want to know when is it greater than or equal to 0, I wanted to include the x-intercepts in the answer, which is why I put square brackets at all the x-intercepts. And then always a round bracket at infinity. So if you were to pick an x value in between either of these intervals, it would satisfy the original inequality. And let me show you another way we could have gotten this same solution. So I'm going to move this up a bit to make room for what we call a sign chart or factor table. This sign chart is just a way of breaking up this polynomial function into different intervals based on where their x-intercepts are. Notice there are 1, 2, 3, 4 intervals, which is why I have 1, 2, 3, 4 columns I'm going to fill out information in the sign chart. You can always start by putting negative infinity on the far left, positive infinity on the far right, and then listing the x-intercepts in ascending order between them. Then we also need a row of information for each of the factors that make up the polynomial equation. Notice there are 3 factors in the polynomial equation. I'll place each of those factors in its own row. And then this is just going to be an organized way of testing values in each of these factors one at a time to determine if the overall sign of this polynomial function is going to be positive or negative in each of the intervals we've created. So in the first interval between negative infinity and negative 5, I have to pick a test value. I'll pick negative 10. If I were to sub negative 10 into this factor of x minus 3, I would get negative 13, which is a negative answer. If I sub it into x minus 5, I get negative 15, which is a negative answer again. And then subbing it into x plus 5, negative 10 plus 5 is negative 5. Again, a negative answer. So what we've just figured out, in this interval between negative infinity and negative 5, any x value is going to make all 3 of the factors that make up the equation, it's going to make all 3 of them negative. So we would have a negative times a negative times a negative. Any odd number of negative factors is going to give a negative result, which verifies that this polynomial is going to be below the x-axis on that interval. So it's not going to be part of our solution set because we want to know when is it greater than or equal to 0. And then we'll just do the same thing for the other 3 intervals. And because we're looking for when the polynomial is greater than or equal to 0, anytime it's positive, which is in these 2 intervals from negative 5 to 3 and 5 to infinity, that's when the polynomial will be greater than or equal to 0. So this sign chart is an alternate way to come up with this exact same answer without having to graph the polynomial. Must know number 10, solving rational inequalities. To solve a rational inequality, step 1 is move all terms to one side. Then combine the expressions together. Then factor your rational expression to be able to determine its x-intercepts and vertical asymptotes. And then make a sign chart to figure out what intervals are the solution to your inequality. So let's have a look at an example. All right, in this rational inequality, the first thing I would do is take this whole term that's on the right and move it to the left by subtracting it. And now I want to combine these expressions together, so I would have to get a common denominator. I'll multiply this fraction top and bottom by x minus 3, and then this fraction top and bottom by x plus 1. And now that they both have this common denominator of x minus 3 times x plus 1, I can combine them into a single fraction. And then let me make a bit of room so I can expand this numerator and simplify. If I do that, this first product is a difference of squares. It's an x squared minus 9, minus this product would be x squared minus x minus 2. And then if I subtract all three terms in this polynomial, and then collect all the like terms in the numerator, it will simplify to x minus 7 in the numerator. And then unlike polynomial inequalities, where at this step we would consider just graphing that function to figure out when it's less than 0, I think it'll be easier for this one just to pick some test values within intervals that we make by dividing it up based on its x-intercepts and vertical asymptotes, since those are the only places where a function might switch signs. So let's actually start by stating the x-intercepts and vertical asymptotes. Well, the x-intercepts are the values of x that would make this rational function be 0. And that rational function would be 0 if the top was 0, and that would happen if x was 7. So we have an x-intercept at 7, and vertical asymptotes are going to be the values of x that make this function be undefined. The function would be undefined if the denominator was 0, which would happen if x was either 3 or negative 1. So there are vertical asymptotes at x equals negative 1, and also at x equals 3. So what I'll do is I'll use a sign chart to divide this function up into intervals based on these values. And then in the sign chart, I need to test values within each of these intervals I've created into this rational function. And I'll do it part by part. I'll sub it into each of the factors that make up that rational function one by one. So I'll give a row to each of those factors. Within the first interval from negative infinity to negative 1, pick any number in that interval. I'll pick negative 100. That would make x minus 7 be negative 107, which is negative. It would make x minus 3 be negative 103, which is also negative. And it would make x plus 1 be negative 99, which is also negative. So in this rational function, I can see in this interval from negative infinity to negative 1, I would have a negative divided by a negative times a negative. An odd number of negative factors gives a negative result, which means this rational function in that interval is negative, so it is less than 0, which means this interval is going to be part of my solution set. Let's check if there are any more intervals where the function is negative, where it's less than 0. From negative 1 to 3, I'll choose a test value of 0, and that makes these factors be negative, negative, and positive, which is a positive result, so that will not be part of my solution set. But from 3 to 7, I'll choose a test value of 5, which makes my factors be negative, positive, positive. A single negative factor is a negative result. So this interval between 3 and 7 is also going to be part of the solution set. So I'll add it to my solution by using the union symbol, or from 3 to 7. And then in the last interval, I'll pick a test value of 10, which makes all of the factors be positive. So the whole rational function is positive, which means in that interval, it's not less than 0. So any x value within either of those two intervals is going to make this rational function be less than 0, which means those are the intervals of values that are the solutions to the original inequality. If you made it to the end of this video, I hope you learned a lot about solving inequalities, and let me know in the comments what you want a top 10 of next.
Jensen